this lecture, we will analyze common gate LNA. And as was pointed out in one of the previous lectures, that when the operating frequency is very small compared with the threshold frequency, then there are three ways in which a MOS can be used for LNA. Out of those three, two ways is basically the common source configuration, and we have already seen those two LNAs in previous two lectures. The third way in which MOS can be used for LNA purpose is this common gate configuration. And we know that for this case, we will be able to make CGS0. And in this analysis also, we will neglect the channel length modulation. So this is the assumptions for this LNA. So we will see what is this LNA. So configuration is this one. So here input is at the source and output is as usual from the drain. And the gate is connected to a DC bias. So for this circuit, we will try to find out the input impedance. Then we will try to find the noise factor. And we will see that for this configuration, once the input impedance is fixed, which is looking from here, and obviously for match condition, it should be equal to RS. So once this condition is satisfied, we will see that we will have no control over the noise factor. So this circuit will be modified so that we can sort of decouple the input impedance and the noise factor. So we will see a modified common gate LNA, and for that case again we will find out Z in and noise factor. So first let us try to find out the input impedance for this LNA. So since the gate is connected to a DC, so this is effectively ground here. So Z in is going to be Vx by Ix. Right. So here, if we keep this output port open, then you can see that here we have open because this inductor is large and reactance offered by it will be large, and it will not allow any current to flow through this. So this Ig, here you can see that will have no path to flow. So in this case, we will not be able to proceed. So what is done is that we include the non-ideality, lossy part of the non-ideality of this inductor, and we say that because of the finite conductivity of the inductor, there will be or resistance effectively in parallel. Very often this R1 is also shown in series with inductor, but here we are going to show it in parallel. So now even if the output port is open, so now you can see that between the drain and this supply, which is AC ground, there is R1 resistor. So here we have drain, and here we will be having R1. And this R1 is typically large. So now we can see that this IG current will flow, and now we can proceed ahead to find out this input impedance. So this is the source node. So to set up the equation, we apply KCL at source. So this is Ix plus Ig is equal to 0. So this implies Ix is equal to minus Ig, which is equal to GMVGS. And since the gate is grounded, so this VGS becomes minus Vs. So this becomes GMVS. And we see that this Vs is basically connected to this Vx. So Vs is equal to Vx, therefore Ix is equal to Gm Vx. So this implies Vx by Ix is equal to Gm, 1 by Gm, in fact. And this is certainly real, and it can be made equal to 50 ohm also, or equal to Rs. So Zin is 1 by Gm, and this can be made equal to Rs. So here we see that Zin depends upon only one parameter Gm, and we will have to make this equal to Rs. So Gm gets defined here for the input matching purpose. When we derive the noise factor, we will see that Gm appears in the noise factor also. And once you select Gm here, you will see that noise factor also gets decided. And that is why there is a strong connection between the input impedance and noise factor for this configuration. Now we will try to find out noise factor. So in this circuit, we can see that we have three sources. One, the source itself. Second is MOS, and third is the lossy part of the inductor. Since we have derived input impedance for this circuit, so we will have to find out the noise factor also for this one. So we will have to find out the shorted output current for each of these sources, and we will use the superposition principle for that purpose. We are going to use the Norton model. So first, due to Rs, and this we will call as IUN. So let us first draw the circuit containing only the noise source due to the Rs. So this is the current we are looking for, ION. And here you can see that R1 is basically short circuited. This end was, lower end was anyway grounded. Now because of shorting, the other end, drain end, has also become ground. So ION is actually going to flow into the MOS. No current will flow through R1. So this current is also ION, and we will be calling this as IN. So from ACL at drain, we find that ION is equal to GM/VGS. And since gate is grounded, so this is GM/VS. So we need to find out the source voltage. So for that, we apply KCL at source node. So here we get IN plus ION is equal to 0, and IN plus GM, this is minus VS is equal to 0. We have already found out ION. Now this IN current is current through this resistor RS. So this end is at voltage VN. This other end, right end, is at voltage VS. So IN can be written as VN minus VS by RS. So this becomes Vn by Rs minus 1 by Rs plus Gm Vs is equal to 0. So this gives rise to Vs is equal to Vn by Rs into 1 by Rs plus Gm. Or this gets simplified to Vn by 1 plus Gm Rs. So this is one way in which we can find out Vs by setting up KCL equation at source. So we could have arrived at this expression for Vs using a shortcut technique. And here note that input impedance is equal to Zin. That means the impedance looking into source is Zin, and this we have already found out equal to 1 by Gm. So what happens is that this entire circuit gets simplified to this one. Here we have Rs, here we have Vn, and this is connected at source, which effectively behaves like resistor with value 1 by Gm. And this is the source voltage that we are looking for. So we could have straightway written Vs as 1 by Gm divided by 1 by Gm plus Rs into Vn, and this will turn out to be Vn by 1 plus Gm Rs. So here you can see that this equation is same as what we derived earlier. So sometimes it is possible to do these kinds of shortcut, but not always. Okay, so we now know what is Vs, so we can substitute here to find out ION. equation 1. Let us call it equation 2. And this we can call as equation 3. From 3 2 implies ION is equal to minus GM Vn divided by 1 plus GM RS. So this is the current, short-circuited current that will be flowing because of the source. Now we have to find out short-circuited current due to MOS. And this we will be calling as IOD. So recall that in the previous two LNA, this IOD used to be equal to ID, the total drain noise current produced by MOS. But in this case, it is not going to be same. So here it will not be equal to IOD. We will see, and region is RS. So we are trying to find out IOD. And once again, you can see that no current will flow through R1. So entire IOD will flow in this direction. And here we can see that we have two currents, IG and ID. So this double arrow inside the symbol for ID only means it is noise. This in no way conveys what will be the direction. So you can assume any direction, but I have assumed it to be in the downward direction. And these, so we can write KCL at the drain. So this will give IOD. This gets splitted into two currents, IG plus ID, where IG is GM VGS and gate is grounded. So this is minus GM VS. Now these two currents, they again merge here at the lower end, at the source in, to reproduce IOD, which ultimately flows through RS. So this source voltage that we see here, Vs, is because of IOD flowing through RS. So Vs is equal to RS into IOD. And this we can substitute here. So this implies 1 plus GM RS IOD is equal to ID. So here we see that IOD is actually, IOD is not equal to complete ID, but a part of it. So this is a surprising result, that why not the entire ID flows through the short circuit, and that happens because of this Vs getting generated here. So what happens here is we have already seen that the gate current is minus Gm Vs, and we found this to be Rs IOD. So here we find that this not the gate current but dependent current source, because of MOS is negative. It is negative. So if it is positive, then it flows in the downward direction, in this direction. But it is negative, that means it actually flows in this direction. So what happens is it flows in this way. So what we find is that this dependent current source, it circulates in this loop. So sort of you can say circulates inside MOS, and that is why what we see is not the entire ID flowing outward, but only a part of it. So the actual KCL now you can see at the drain will be that IG is flowing in this direction, and IOD in this direction. They are merging. So IG plus IOD, these two, they are merging to make it equal to ID. And magnitude of IG we have already found out. It is Gm Rs into IOD. And here we already have IOD is equal to ID. So 1 plus Gm Rs IOD equal to ID. Right. So because of this circulation that we see that only a part of ID goes out, and remaining part it flows in this circuit. So the part that flows or the circulates is equal to Gm Rs ID by 1 plus Gm Rs. So it is this much of current which actually circulates in the MOS, and this circulation is arising because of feedback arising because of degeneration. Right? And this degeneration was not there in resistively terminated resistive feedback LNA. So that is why the entire ID was able to flow out. Here we have equation 4 for ION. Here we have 5 for IOD. Now we need to find out what is the current due to R1 resistor. So we are going to use Thevenin model. It will be easier to solve with this. So this I1 we want to know, and this is the noise current source due to R1. So again, R1 is short circuited at the both the ends, so there is going to be no current flowing through R1. And here also it means that this entire I1, it is going to flow like this. So here also IO1 is going to be equal to I1. So this is the kind of response that we have been getting for drain current in the previous two LNAs. So now we know all the three currents. So now the next step will be to find out the total mean square current. Again, all these three noise sources, they are physically independent entities. So these are going to be uncorrelated, and their mean square, combined mean square is simply going to be sum of individual mean squares. So the total power going to be a constant dependent upon the load and the output impedance for the Norton model into IO mean square, and output power due to RS is going to be same factor multiplied by its mean square current. So therefore the noise factor F is going to be total mean square divided by ION mean square. So this will turn out to be 1 plus IOD mean square plus IO1 mean square divided by ION mean square. So now we can substitute each of these currents in terms of their source, in terms of ID for this, in terms of I1, in terms of Vn for the denominator current. Now we can substitute these currents in terms of their model, conductances and resistances. Which will simplify to gamma GD0 plus 1 plus GMRS whole square divided by R1 whole divided by GM square RS. And this will become finally gamma GD0 divided by GM square RS plus 1 by GM RS whole square into 1 by RS R1. So this is the complete expression for the noise figure, actually noise factor. So here we see that once we select G1 by GM is equal to RS. So for match case, 1 by GM is going to be equal to RS. So this will simplify F to be 1 plus gamma GD0 by GM plus 4 RS by R1. And 1 by GM is again RS. So this becomes gamma GD0 RS plus 4 RS by R1. So here we can see that gamma and GD0, they are determined by the MOS. RS is determined by the source, which will be 50 ohm, R1 determined by inductor. So once we make this match condition, the noise factor gets fixed. There is no way we can change it, right? So what is done is then we introduce a modification in this circuit so that there is a decoupling. That means there is an additional parameter using which we can decide Z in independent of the noise factor. There is some degree of freedom in using Z in. So we introduce a feedback at the gate. So here we introduce a voltage feedback at the gate using a network which will be designated by alpha, its transfer function. And of course, we will find out Z in here at the source. And there are few properties of the feedback network, this alpha, that we will assume for analyzing this circuit for its input impedance and for the noise factor. So it senses voltage and feeds voltage. So this is also called voltage feedback. So the first property is the input impedance of this feedback network is infinite. So here we have input impedance. That means this current is 0. And this is feedback network, so its feedback factor is alpha. That means if we have Vi here, Vo is going to be alpha Vi. This is the meaning of alpha. And we will see that this alpha need not be equal greater than 1. And in the beginning, we will just assume that this is noise less. Later on, we will remove this restriction. So now let us find out Z in for this new circuit. So now between drain and gate, we have this feedback network. So here ZD is actually this whole thing. So at this stage, it is a parallel combination of L and R1. So let us proceed with this. Then I will come back to this point again. So when we apply this ACL at the source, so Ix is equal to minus GM VGS. And here we have gate voltage. So this gate voltage, if this is the drain voltage, then the gate voltage, which is the output of this feedback network, is going to be alpha Vd. So Vg is equal to alpha Vd. So alpha Vd minus Vs. Now we have to find out what is Vd. So we can see that this Vd is voltage at the upper end of this ZD, the impedance, and this Vd is equal to minus ID ZD. Now we have to find out ID. So ID, in general, there will be KCL at this drain end, and here we have ID, here we have IG, but this current is equal to 0. So ID is going to be equal to IG, this the dependent current source. So for ID, what we find is that this is equal to IG. So therefore, VD is minus IG ZD equal to minus GM VGS ZD VD. Or and that is okay, but that is not going to lead to meaningful things. So here we find that Ig is minus Ix. So in fact, there is no need to go to this stage. From here, we could go to Ix ZD. So now we can go back to this equation, equation 7. So Ix is equal to minus Gm alpha ZD Ix minus Vx. So this Vs is nothing but equal to Vx, because these two nodes are shorted. So here we have the final equation, and this we can solve for Ix. So this becomes 1 plus Gm alpha Jd Ix is equal to Gm Vx. So this implies Vx by Ix is equal to 1 by Gm plus alpha Zd. So the new input impedance is 1 by Gm, which used to be the earlier one. So let us call Zin dash plus alpha Zd. So of course this should be real. So there are two ways in which this can be converted to real. One is which we have already done, that the reactance suffered by this uh, inductor is very high. So what will happen is entire current will flow through this R1. So this parallel combination of this will approximate to R1. So this is one way in which ZD will, or ZD can be interpreted as real, 1 by Gm. So it becomes alpha R1. This is one interpretation. Second interpretation is that one can always include a capacitor, which could be a combination of external and the parasitic capacitor of the inductor L. And in that case, we can talk about frequency, where this L and C, they will cancel out each other, and what we will be left is only R1. So that is also possible. So second interpretation is this one, that we have a CE here, so that this is at equal to R1 at omega square is equal to 1 by LC1. So another way of getting this real is at omega square is equal to 1 by LC1. So now here we can see that we have two parameters, Gm and alpha, to decide input impedance. Now let us try to find out what will be noise factor. And here, because R1 is large, so you can see that this alpha is less than 1. Because we want Zin dash to be equal to 50, and R1 will be typically a lot more than 50. 1 by Gm is anyway positive number, so alpha has to be less than 1, in fact significantly less than 1. Now let us find out the noise factor. So first is shorted current, shorted output current due to RS, which is ION. So earlier, gate was grounded in the previous version where alpha feedback network was not present here. But here you can see that when we add this alpha and when we are trying to find out this short circuited output current, so we are grounding this drain. That means the input of this feedback network is 0. So that means output is also going to be 0 volt. So here also the gate remains grounded. So using this argument, one can guess or even claim that the circuit, at least for finding out noise contribution of this RS, remains same as it was earlier. And in fact, this is what it will turn out. So one can carry out the analysis similar to what was done earlier. And it will turn out that even here, the short circuited current remains same as the previous case. Since gate is grounded, as was the case earlier. Right. Now, if we go for finding IOD, that is due to short circuited output current due to ID, the MOS, and here the model is going to be like this. So here also, once again, we find that input voltage is equal to 0. So gate voltage continue to remain 0. And moreover, any IOD current that flows will pass either through this path or through this path. No current goes into this feedback network, which is one of the assumptions that we have done. In fact, that assumption is valid here also. This I is 0. That is why this entire ION was equal to this GMVGS. So not only this input of this feedback network is 0, leading to gate voltage equal to 0, but also that the current into it is 0. So it never alters the KCL equation that we wrote for the previous version. So it continues to maintain gate 0 and same KCL at the drain. So here also one can argue that IOD is same as the previous case. But one can always work out the entire detail. And now when we try to find out noise current due to R1, so here we find that again this both the ends of this source are grounded. So the entire current is going to take this path. Again, this is 0, no current into it. So similar situation as the previous case. So IO1 is equal to I1. So we found that all the three currents after including this, they remain same. And keep in mind, this is the case for by neglecting the noise contribution of the feedback network. So the noise factor, therefore, F remains 1 plus IOD mean square plus IO1 mean square divided by ION mean square. And this we have already derived. Gamma GD0 by GM square RS plus 1 by GM plus RS 1 by RS R1. So here we find that this is independent of the feedback factor alpha. So using alpha, one can choose Z in, and then here we have freedom of changing F with the help of GM. So here F is function of GM, while Z in can be determined with the help of alpha. So now it is possible to a very good extent, independently choose these two parameters. Now one can say that what will happen if we include the noise factor of alpha. So of course, that is definitely going to alter the expression for the noise factor of the amplifier. So we are going to take a very simple model for this feedback network. So this is noisy, and this we are going to substitute by input referred noise voltage source. In this case, now this is noiseless. So this is definitely not going to alter the input impedance of this new circuit, modified one, but this will alter the noise factor. So now there are going to be four noise sources: RS, uh, RS, R1, MOS, and the alpha. So noise contribution of each of these, they are going to be same what we have already derived. Only thing is that noise contribution of this network has to be found out, so we can carry out this analysis. Let us call this short circuited output current as IU alpha. So this VD is 0. So input to this alpha network is V alpha. So output is going to be alpha into V alpha. This is going to be the output, and current I alpha is going to be 0. So this entire IU alpha is going to be equal to GMVGS. Therefore, IU alpha is equal to GMVGS, and the gate voltage is alpha into V alpha, and here we have minus Vs, and the same current flows here also, and it is responsible for Vs. So this is GM alpha V alpha minus RS IO alpha. So here we have IO alpha is equal to GM alpha V alpha minus GM RS IO alpha. So therefore 1 plus GM RS IO alpha is equal to alpha GM V alpha, and IO alpha is equal to alpha GM V alpha divided by 1 plus GM RS. So if we find out the noise factor in presence of this alpha or common gate, so this will be IUN mean square plus IUD mean square plus IU1 mean square plus IU alpha mean square divided by IUN mean square. So this becomes 1 plus IUD mean square, IU1 mean square, IU alpha mean square, IUN mean square. So out of this, you can see that the first two terms here and here, they were present in the older version. So we have this thing, plus we have now this additional factor. So this is clearly more noisy. So this is F alpha CG is equal to FCG. This we have already derived. Plus we have the additional factor. And here you can see that what we have here is this we can substitute, and 1 plus GMRS was present in the expression for IUN as well. So this will become GM square VN mean square in the denominator, and in the numerator we will have alpha square GM square V alpha mean square. So we have alpha square, and we can assume register to designate this V alpha mean square, and the expression will be this. So here what we have done is V mean square alpha has been taken as 4 KT R alpha delta F. So this is equivalent register to account for the noise produced by this. And as was pointed out, alpha is less than 1. In fact, it is going to be significantly 1, less than 1. So alpha square is going to be definitely very, very less than 1. So the contribution of this is not going to be very large. So this is going to be small. So this is how we can decouple the input impedance and noise factor for common gate LNA.